And my look of panic there for a moment was it looked like my slides for this lecture had vanished, but they hadn't. So we're not in as bad shape as I thought. You've probably discovered by now that we try to bring the handouts from the previous and current lecture to each lecture. After a day or two of that lecture, those older handouts will be available either online or through the main biochemistry office. So we'll try to have the current ones available, but not necessarily a complete supply of the whole semester. Please only take one copy each. Don't take a fresh one every time you come to lecture. The lecture from Friday is not yet online, but should be later today. And I have good news from the bookstore, which is that the textbooks are in at the bookstore. The woman there has said that if you don't see them on the shelf, to let a clerk know, because as you can imagine, they can't put all 200 copies on the shelves at once. So they are in stock, and if you don't see them on the shelf, please just ask someone to help you with that. Are there other questions about the course or course organization before we start talking about aqueous chemistry? Okay. I am still getting to learn the new computer here. They've given us more computing power, and I will try to make good use of that extra computing power, but I'm still kind of feeling my way through it. So it may not be in full force yet for this lecture, but I hope to keep drawing on it in a more effective way as the semester goes on. So in looking at this first slide here, I'm sharing with you a joke that was from my first ever biochemistry lecture. That when he did it more effectively with covering up part of the answer first. What would life be like without water? Crisp. It turns out that all living things that are actively living have enough water in them to have at least some liquid water as opposed to water bound to other molecules. And it's not an accident that water is essential for life. And there are several reasons why water is essential. One is it is an amazing solvent, and we'll take a look at some of the ways in which it acts as a solvent as part of this topic. Secondly, the interaction of molecules with water is one of the major driving forces behind the structure of proteins and of membranes. And so the chemical properties of water are going to be related to the structural properties of all those other things as well. There's no new handouts if you got them on Friday. So Tim, maybe you could take a few up if there's anybody who didn't get them on Friday. Thanks very much. There are some up there already? Thanks. Cool. Okay. And then another way in which water is essential for life is acid-base relationships. It's going to turn out that a very large fraction of things in living systems depends on either the right balance of acid and base or exploits acid or base as part of the catalytic mechanisms and so on. Some of the ways in which we see the ways that life is tied to liquid water specifically, because of course water could be gas or solid, is actively living cells only occur if you are in the range where liquid water exists, and so you don't see actively living cells below the freezing point or actively living cells above the boiling point. We also see it in terms of what kinds of chemical reactions get used by living systems. So water turns out to be important in a lot of ways. We, human beings, are about 60% water. Most living things are more water than not. If you look at a cell is typically about 50% water. And what's striking about that is if you've done any protein chemistry at the crystallography level, a protein crystal is also about 50% water. So our cells are not this dilute sack of free-floating bits like a weak minestrone. We're much more like a beef stew. So cells are fairly densely packed with stuff, but they have water as about half the volume, sort of filling in the cracks, if you like. And this is showing you sort of that distribution of things, about 40% not water of one kind or another. Another 40% of our mass is inside the cells. We don't have as much in our circulation as you might think, only about 5% is in the blood and so on. And then another 15% that's just sort of in between and around and about, things like the lymph and so on. Now, what makes water so extraordinary is the structure of the water molecule. And water is an intensely interesting molecule despite the fact that it only has 3 atoms. And we're going to start looking at water in the way we're going to look at other things to see how structure and function are connected. So here we have a structure of a water molecule. And you have your oxygen atom there in the middle. You have the 2 hydrogen atoms at 2 of the 4 points of a pyramid. Another thing that makes this an interesting structure is that the bonds here between the oxygen atoms and the hydrogen atoms are not symmetric. You remember we talked about electronegativity, that you had hip casino, so oxygens at one end and hydrogens on the other, so they're at the opposite ends of electronegativity. This is going to be a fairly asymmetric bond, and that's what happens, is that the oxygens get more than an equal share of the electrons, so they have a partial negative charge, and the hydrogens don't get a complete half share, so they have a partial positive charge. And what that means overall is that the water molecule is a polar molecule. It has both polarity in its bonds and polarity for the molecule as a whole. And because there are these partial positive and partial negative charges on the molecule, it's capable of making bonds to itself of a kind called a hydrogen bond. And a hydrogen bond, we're going to see, is simply any partially positively charged hydrogen to anything with a partial negative charge. And in looking at liquid water, there's an uncounted number of these within the water mass itself, up to 4 per water molecule. And this is showing you those partial positive and partial negative charges. Here we've left out the other 2 electron clouds, but those are capable of, those are also part of the picture. One of the other things to think about here is that the molecule as a whole is polar. That is, looking at this end of it is partially positive, and this end of it is partially negative. So each bond is polar, and the molecule itself is also polar. And both of those features contribute to properties of water that are going to be very important. This is a diagram of a hydrogen bond. We're going to meet hydrogen bonds in many places, but this is the first one we're meeting them. So there's the oxygen with its partial negative. Here's the hydrogen with a partial positive. And the hydrogen bond is simply this weak electrostatic bond between the hydrogen, the positive, partial positive charge and the partial negative on the oxygen. This alignment will affect how strong that bond is. If the hydrogen is sort of pointing straight at the oxygen, it's a stronger hydrogen bond. The distance here between the 2 of them will be a measure of the bond strength. So there are some instances where the distance between this oxygen and the hydrogen and this hydrogen and this oxygen are more or less equal. Those are called low barrier hydrogen bonds, and they tend to be a little tighter. These hydrogen bonds are what underlie the structure of both solid water, which you would expect to have a structure, and liquid water, which you may not have thought of having a structure. So if you look at ice, which is solid water, all 4 potential hydrogen bonds are occupied. And in order to do that, you can see it has to make kind of an open structure overall. In order to make all those things fit in there, it kind of has to be spread out and space it a little bit. In water, any one water molecule may have up to 4 hydrogen bonds. Most of them have at least 3. Those hydrogen bonds are much shorter lived than the ones in ice molecules. But because the ones in water are short-lived and sort of constantly tweaking each other and readjusting, liquid water is actually denser than ice, which is a very strange thing. In almost all other circumstances, the solid is denser than liquid. Water is an extremely unusual thing. If people know of another counterexample, I'd be interested in hearing it, but it turns out to be crucial for life. The fact that each water molecule has 3 to 4 bonds to other water molecules also makes water very cohesive. much more cohesive than most liquids would tend to be. And does that make any difference? It certainly does. The polar character of the water and the multiple hydrogen bonds that the water molecules make with each other give water extreme values, unusually high or low values for a number of characteristics. One is surface tension, the tendency of the skin of a droplet of water to hang together. Here you can see a bug that's walking on the water because of the surface tension. Water has a higher melting point than you'd predict for its molecular weight. It has a higher boiling point than you'd predict. It has a high heat capacity. That is, you can put more calories of heat into it before it changes temperature. And that helps to make it a good heat buffer so that living systems are somewhat buffered from heat changes. The polar character of the molecule is also part of what makes it a very good solvent, and we'll be looking at that in a little bit more detail too. And the fact that ice floats means that the oceans don't fill up with ice. If ice sank, you'd form some ice at the North Pole, it would sink, more ice would form, it would sink, and so on, and you'd eventually, fill up the oceans from the bottom up. But ice floats, and so we have a chance of having liquid water underneath the ice layers, which can then continue to support life even though the top layer might be frozen. This is giving you a little bit of a comparison of some of the strengths of different kinds of bonds. Over the course of the semester, we'll be talking about molecules that have covalent bonds, where they're sharing 2 electrons equally. Covalent bonds are the most typical ones that, we think of when we think about proteins and nucleic acids and so forth. Ionic bonds are when oppositely charged groups are aligned in ways that let them kind of stick together. We're going to see these playing a role in protein structure, for instance. And here are so that's the covalent bond, the big and strong one. Here's the ionic interaction. Maybe a fifth as strong, so it's not as strong as a real covalent bond, but still definitely there. A hydrogen bond is rather weak by comparison, but if you have a lot of them, it starts to add up. Hydrogen bonds are formed between water molecules, but they also can form between hydrogen and oxygen in other molecules. They can form between hydrogen and nitrogen, and even hydrogen and sulfur. So the hydrogen bonding capacity is going to be distributed in a wide variety of molecules, not just in water. And van der Waals interactions are the very low-strength, short-range interactions between one molecule and another by virtue of just being a molecule. It's easy to be impressed by a few strong things, but we need to remember that many weak things can add up to being stronger than a few strong things. And so this is a picture, you may have seen this before, of Gulliver in Gulliver's Travels, where the human being is completely pinned down by the little Lilliputians because there's so many of them. And that's kind of the key thing to remember about things like hydrogen bonds and van der Waals forces, is they are not as strong or as short as the covalent bonds, but there are a great many of them, and so they end up playing an important role as well. This is just showing you some comparisons in the lengths of the different bonds. Here's the covalent bond, not quite twice as long for a hydrogen bond. This is showing you that a van der Waals interaction is sort of the effective surface of a molecule. You're not going to get much closer than that. This is showing some other examples of where hydrogen bonds are going to be extremely important, also other kinds of electrostatic interactions. Here we're looking at a base pair in a DNA molecule. You've got a cytosine and a guanine. And you can see here hydrogen bonds forming between the two bases. And so you can see aligned there that they have 3 hydrogen bonds forming, and it's going to turn out that these hydrogen bonds within the molecule are going to play a key role in genetic information. Here's an example of van der Waals forces. London dispersion forces are transient interactions where if a molecule has sort of flickered into a partial charge, it can induce a partial charge on the adjacent molecule. So it's a very transient and very weak interaction, but part of sort of the background texture of molecules dealing with each other. Now, I mentioned at the beginning of the lecture that water was extremely important as a solvent. And so we're going to take a look at why it's such an important solvent. And it has to do with its polar character. Here we're looking at a water molecule interacting with an alcohol. So you remember I said to sort of refresh your memory of the functional groups. This OH here is an alcohol group. And you can see here that the partially positive hydrogen has formed a hydrogen bond to the partially negative oxygen of that functional group. Here is another hydrogen bond between a water and an amine group. And that reminds me, somebody asked about an error, and I want to point it out while it's fresh in my mind. In the first chapter, looking at the functional groups, the very first problem, the last group in the figure is actually a secondary amine, not an imine. Maybe I should just write that down. So I don't know how many of you are that involved with it. Chapter 1, number 1, last group equals secondary amine. She was pointing out that an imine has a double bond. So, just in case anyone else was worried about it. And, oh, the other thing is, people didn't remind me until after the lecture that the lights were too high. If I do that again, please nag me faster. Let me try that one. Is that going to work? No, that's not good. Have they still got the spots on the screen? That's amazing. Can you see that all right now? Yes? No? Raise your hand if you can see it okay. If you have problems, raise your hand. Okay. If this starts to be too bright, let me know and I'll turn it down further still. And I'll see if we can get some way. AV person, hi. Is there any way to turn off the spots that are on the screen, for instance? Well, he was working on that. We can go back to water, which is more interesting. I mentioned at the beginning of this talk that the cell is about half water. And so what that means is there's only a few water molecules around any given molecule. Only a few water molecules around any given molecule. And this diagram in your book is a nice way of capturing that. It's showing you how densely packed the cytoplasm is. Most diagrams of the cytoplasm don't make it anything like crowded enough. And so it's important in the cytoplasm that the water is there as sort of a lubricant or a bumper to keep the molecules of the cell from just simply being completely squished together. But it's really a densely packed place. Okay. So the polar character of water makes it very good for solvating ions. So here's a sodium ion. It itself has a positive charge on it. So the water molecules around it are going to tend to point the partial negatives towards that positive. Here's a chloride ion, which has a full negative charge on it. The water molecules around that are going to tend to orient so that the partially charged hydrogens are pointing towards it. So these are little cages of water molecules. And one of the consequences of that is that ions in the cytoplasm have a larger diameter than just the atom itself. There's a little shell of water around most of them. It also makes water good for solvating polar compounds that don't have charges. Here's a glucose molecule in a ball and stick. And you can see all of these oxygen atoms. Each of those oxygen atoms has a partial negative charge. And so the partial positives of the water, hydrogens, can then readily help put that into solution. And if any of you have ever made a sugar syrup for candy or something, you know that you can put almost an equal volume of sucrose sugar into water and have it actually go into solution. So it's a very good solvent for them. Questions? I can't believe they still have the spots on the screen. So that part is straightforward. The solvent properties with polar and ionic things is intuitive. You know, opposites attract. That's not hard. The other important way in which water behaves as a solvent is by supporting what's called the hydrophobic effect. And the hydrophobic effect is going to be important for a lot of different biological structures, so it's worth understanding how it works. What it literally means is phobic, hating, or fearing hydros, water fearing. And now, these are all molecules. They don't really care. I mean, they don't have emotions. But it's as if certain molecules reacted to avoid the water. By comparison, if something's polar, we call it hydrophilic, water-loving. Now, if you take a compound like, for instance, here, dodecane, which is a nonpolar compound. It's carbons and hydrogens. Carbons and hydrogens are fairly close on the electronegativity scale. Not a lot of distribution of those electrons asymmetrically. A fairly nonpolar molecule. There isn't either a positive or a negative charge for the water to orient towards in particular. And so it constrains the extent to which water can interact with that. And here's a diagram of how to think about that in terms of how that would affect overall the entropy of the solution. So here we have a nonpolar molecule. If we try to put that individual molecule into water, what we can detect with appropriate methods is that there's the water that's closest to it is not free to move in quite the same ways in which water around a polar molecule or whatever would be. And so if you were to have more than one molecule that was nonpolar, so here we have a number of water solute molecules, a number of molecules we put into the water. Each of them has their own layer of water that's not very free compared to the ordinary water. If all of those nonpolar molecules bunch up like this, they are more ordered, it's true. But there's a smaller amount of water around them that's constrained. And so although it's not obvious, this is the pattern that's favored by entropy. So the hydrophobic effect is driven by considerations of entropy, of disorder. That if you compare the dispersed pattern to the one where the nonpolar molecules are together, the molecules themselves are more ordered, but the water is more disordered. And so the hydrophobic effect is driven by entropy. And why does that matter? We're going to see the hydrophobic effect in a number of extremely important places. The structure of membranes is going to depend on the hydrophobic effect. The structure of proteins is going to depend on the hydrophobic effect. Some aspects of nucleic acids depend on the hydrophobic effect, but they also depend on something called stacking interactions. So we're going to see it in several very important places, and it's worth having a sense of comfort with the hydrophobic effect. Now, just to make life a little more interesting, there are some molecules that can't make up their mind. They're called amphiphilic. So they love both of them. They love water and they hate water, or whatever. So here there's a polar end at this end. There's a little carboxylic acid, which is clearly a very polar end. And here's the tail of it that is nonpolar, that's hydrophobic. And so within one molecule, you're going to have some parts that are hydrophilic and some parts that are hydrophobic. But the polar character will always be a good guide to you on that. The more polar it is, the more hydrophilic. The more nonpolar, the more hydrophobic. Now, the fact that you can have one molecule have both kinds of relationships with water means that you can use that property to drive the formation of structure. If you have more than a few copies or more than a few molecules of an amphiphilic compound, those hydrophobic tails will try to sort out away from water. And you can see that taking a number of different patterns here. So, for example, if you just have something like this could be, for instance, a fatty acid. It's got a nonpolar tail and a polar head group. It will tend to sort out from water in a pattern like this, called a micelle. And you can see here the polar heads that are in contact with the water, the nonpolar tails that are in the center. If you have a differently structured amphiphilic compound, polar head but with two tails, it may well make a group of structure like this. And this is called a lipid bilayer. So this is one example of a lipid. It's a bilayer because there's one layer of lipid pointing that way and a second layer of lipid pointing this way. But again, the hydrophobic parts have sorted out. The hydrophilic heads are in contact with the water. So why do you think it is that the ones with a single tail make the micelle compared to the two tails making a bilayer? The shape, exactly. Like so much of biochemistry, the shape is going to make the difference. In the one with the two tails, it has to spread out as a layer and have enough room to accommodate those tails. Whereas in the case of the ones with a single tail, the head's bigger than the tail, and the micelle accommodates that shape relationship. Now, lipid bilayers are going to be extremely important in membranes because they constrain the diffusion of polar compounds. Here's a lipid bilayer that's been made into a vesicle. That is, it is a lipid bilayer here. You can see that. But it's a balloon of lipid bilayer. It's a completely enclosed space of lipid bilayer. And since this interior of the lipid bilayer is hydrophobic, things that are polar don't interact well with it. And so a lipid bilayer is going to be able to prevent salts, proteins, most metabolites from moving through it. So it provides a barrier function. And this is just sort of showing you that diagrammatically, that diffusion would follow what's called the law of mass action. The law of mass action is if you've got more here than there, you're going to tend to go from here to there. A lot of heat there, a lot of cold there, heat's going to flow that way. High concentration of sugar, low concentration of sugar, it's going to flow that way. A lipid bilayer prevents diffusion from happening just by mass action. What about nitrogen gas? Would you guess that it could diffuse through a membrane? Anyone want to take a stab at it? Sorry? Yes. Okay. Want to give an explanation for why you think it would? Because my neurobiology professor told me. That's not a bad answer. She said her neurobiology professor said it will. If we look at the structure of nitrogen, you've got two atoms that are identical, and so there's no difference in electronegativity, and so the bond is symmetric. And so it's a nonpolar compound. So nitrogen gas is a nonpolar compound. Oxygen gas is a nonpolar compound. And so they both can diffuse through a membrane without any particular difficulty. Now, a water molecule we know is a polar compound. And it was thought for a long time that even though it was polar, it was so small it could just slip through the membrane because it was observed that water did get through membranes. I'll try to remember to turn that off, sorry. It's just saying it's 4 o'clock. It turns out that there are channels for water, and we're going to see those later on. So the idea that a polar character should prevent it from going through the lipid bilayer, in fact, is still a pretty good guide to things. Well, because we have membranes that, in fact, can constrain the movement of ionic and polar things, it means we have the potential for having an interior environment that's different than the outside. And it turns out that that's the case. And if we look at what's inside of cells compared to what's either in our extracellular medium or the ocean, they're quite different. So if you look inside a cell, there's a great deal of potassium and a little bit of sodium and a little bit of chloride. If you look at the ocean or extracellular fluid, there's much more sodium than potassium and quite a bit of chloride. The extracellular fluid is not too bad a mimic of ocean water, actually. And you can see that this is looking more or less electrically neutral. What do you suppose is balancing out the positive charge of the potassium in cells? it's going to turn out that there are a lot of negatively charged metabolite molecules. ATP has negative charges on its tail. A lot of small metabolites are acids and so on. So it's going to turn out that there are a lot of metabolites that can counterbalance the potassium charge there. So now we need to think at least a little bit about acid-base chemistry. So far we've just talked about water molecules as being polar, which they are, but these polar molecules can actually have that bond stretch enough to break, in which case that simple water molecule with 2 hydrogens and 1 oxygen can dissociate into 2 ions. And so one water molecule can make a hydroxide ion, OH minus, and it's often represented as a proton, H plus. In reality, it's always going to have a water molecule associated, almost always going to have a water molecule associated with an H3O plus. And what this means is that you can have what's called proton jumping, where if this protonated water molecule or hydronium loses a hydrogen to this one, it can bump a hydrogen off to there, which can bump one to there, and so on. So the positive charge over here can show up as a positive charge over there. It's not the same hydrogen atom that's doing it. But you can have a propagation of the charge without having an actual movement of the hydrogens very far. I'm about to get into a few equations. Don't panic. I am not going to ask you to solve numerical problems. I will ask you in the course of the semester to feel comfortable with the qualitative answers. If for you the easiest way to get there is to actually solve something, please feel free to. But for most of these things, what's needed is a qualitative sense of what's going on, and I will try to present the math that way. I found that there are sometimes people who can solve problems wonderfully that still have no qualitative sense of it and therefore have no intuitions about how to apply it. And really that's what I want, is I want you to feel like you can use this in the context of biochemistry. So you're not going to need calculators on any tests. It's all going to be qualitative. But do try to follow it, because I'm going to try to point to the most important parts of the equations as we go along to give you a real sense of what's happening. You may remember from general chemistry that things that can dissociate can have their tendency to do that described by a dissociation constant. And so the product of the H pluses and the OH minuses over the undissociated water is going to be a constant quantity. That is, if there's more protons from something or other, there'll be fewer of the hydroxyl ions. More hydroxyl ions, fewer protons, the product will be the same. In most solutions, in most circumstances that we work with, you can treat the water as having a constant concentration. Chemists can work under situations where water concentration changes. Biochemists, not so much. And so we can treat that concentration of water as if it were a constant, in which case we can talk about the water constant as simply being the product of the concentration of protons and the concentration of hydroxyl ions. Now, that product is a very small number. It's 10 to the minus 14th. Or another way of thinking about that is that if you have a neutral solution with equal amounts of the two things, you have 10 to the minus 7th molar protons and 10 to the minus 7th molar hydroxyl ions. Not very many. This is showing you that reciprocal relationship between them, that if you have a lot of protons, you don't have very many hydroxyl ions. If you have a lot of hydroxyl ions, you don't have very many protons. But the product is always going to be that 10 to the minus 14th. So water does dissociate, but not very much. Since it's such a large number, large negative number, people devised the idea of pH. Since the concentration of hydrogen ions ranges over 14 orders of magnitude, this is a way of trying to kind of handle that in a little more compact way. pH of a solution is the negative logarithm of the hydrogen ion concentration. So we're going to use pH to monitor hydrogen ion concentrations over that whole spectrum, bearing in mind this complementary relationship between hydrogen ions and hydroxyl ions. here we are at neutrality in the middle. It would be 10 to the minus 7th hydrogen ions, 10 to the minus 7th hydroxyl ions. That's neutral, so that's a pH 7. So pH 7 is neutral. That may not be intuitive, but it's true. What it means is that whenever the pH is smaller than that, we have an excess of hydrogen ions. And the smaller the number, the greater the excess of hydrogen ions. So the smaller and smaller the pH, the more and more and more hydrogen ions around. If we get above neutrality, if we get pHs larger than 7, we're now getting into ranges where there's an excess of hydroxide ions. And everything above 7 is going to be a basic solution. All living systems have a pH range that they prefer. They have a pH range that they can tolerate. And pH of a solution can be changed by changing the amount of acid or the amount of base in that solution. So if you add acid to a solution, you're going to lower the pH, increase hydrogen ions. If you add base, you're going to raise pH. In this case, we're using the definitions of acid and base, that an acid is a proton donor and a base is a proton acceptor. So just to take a couple of examples, here we have our water molecule. Here's hydrochloric acid. If we add hydrochloric acid to water, we're going to get H3O plus and Cl minus. So we now have an increase in the H3 plus or the H plus. It's an acid. It's going to lower the pH of the solution. It's going to increase the concentration of protons. Here's sodium hydroxide with water. And when it's completed its reactions, you're going to have did I drop something out of here? I did. I'm sorry. Right, I'm sorry. So here's a solution. Here's a solution where we have some protons around. So this is before we put in the sodium hydroxide. This would be acid, but we're going to add to it sodium hydroxide. And when we add the sodium hydroxide, those two will interact until we have sodium and some water molecules. So we have fewer protons around. We're going to a more neutral solution. One of the hydrogen atoms from here reacted with that OH. That's why we have two water molecules here and leave us with a sodium. So this was a proton acceptor. The sodium hydroxide here functioned as a proton acceptor. So we talked about pH as a way to measure proton concentrations. We looked in that previous slide at two examples of either acid or base. Both of the ones we looked at are what we call strong acids or strong bases. That is, when you add them to water, they completely dissociate. But many things don't completely dissociate. Many of them dissociate partially. And we need a way to think about or to talk about that. And here we have an example of acetic acid in water. And it can go back and forth between acetic acid in water and hydronium plus acetate. So this is an ion here. It's acetate. So this is a reversible reaction, and it's going to tend to shift back and forth depending on what you're adding to the solution. We can describe its tendency to go through dissociation with this equation, with a constant. Here's the acetate and the hydronium ions, the ionized products at the top, and then the unionized reactants at the bottom. If we again pull the same trick, that the concentration of water isn't going to change much, we can hold the water as a constant and talk about an acid dissociation constant in which the acetate and the hydronium ions product have a constant relationship to the concentration of the acetic acid itself. And so this is going to give us a way to think about the tendency of things to dissociate. Those can be big numbers, just like the concentrations of hydronium ions got to be big numbers. And so we used pH to control the hydrogen ion concentration range. We're going to use pKa, to think about the tendency of dissociation. So pKa is the negative log of the acid dissociation constant. And in the case of acetic acid, the pKa is 4.76. So it will tend to bring a pH down. If you have a large Ka, if you want to go back, let me see if I can go back a slide. In other words, if you have a large Ka, if this number is large, that means you're getting a lot of this dissociated product there. So a large Ka, it's a compound that tends to dissociate. It means it'll have a smaller pKa or be a more or stronger acid, if you like. Again, not completely intuitive. These are just some examples of pKas to give you a little bit of an intuition for them. I'm not going to walk through all of them because they're not equally important to biochemistry. Some of these are more important in a lab. But two that are going to be relevant in biochemical terms as opposed to doing experiments are acetic acid. So here is acetic acid, and its pKa is about 4.76. So towards the acid part of the scale. Some of these other things in here are often used as buffers. Here we have ammonium ion. Its pK is 9. It's towards the basic end of it. It's going to tend to be acting more like a base. So there is a relationship between the pKa of a weak acid and the solution's pH, the overall concentration of hydrogen ions in that solution. So if we go back to that overall relationship of a weak acid and its conjugate base and the proton, here is the Ka again, and somehow or other, despite everything I did, the line vanished. There should be a line underneath here between the top and the bottom terms. You don't want to know how long I tried to get that line in there. I don't know what went on. I'll see if I can get that corrected before I put it online. We can extract or rearrange it to find out the hydrogen ion concentration by just rearranging. And if we rearrange it, we now see that the hydrogen ion concentration is going to be equal to the acid dissociation constant times the weak acid concentration and its conjugate base divided by its conjugate base. But we've been talking in pKas and pHs, so we need to convert this to negative logarithms. So the pH of a solution ends up being the pKa for that weak acid and the logarithm of the conjugate base to the weak acid. And I'm not going to ask you to solve problems with this. It's rather that I want you to understand that the tendency of a weak acid to dissociate is going to affect the solution that you've been putting it into. Oh, I'm sorry. I think I see what happened. The previous one was one I was working from. This has the same content with slightly different formatting. A number of the functional groups that I showed, that you saw on table 1.1, are capable of being ionized. And some of them are going to be very important in when they are and when they aren't ionized. And so I thought I would just walk through for a moment on a couple of the most important ones. So here's a carboxylic acid, and here is a primary amine. In a solution whose pH is less than 2, there's going to be a lot of protons around. It's a proton-rich environment. Things will tend to be protonated. And the carboxylic acid is itself the protonated form for this. When the amine gets protonated, we now have it in the conjugate base form. So here is the NH3+. If we go out to a pH of 11, where there's a lot of OH minuses, there aren't very many H pluses, it's a proton-poor environment, the carboxylic acid can lose that proton and become a carboxylate. This protonated form can lose its proton and become, again, the primary amine. both of those pHs are fairly far away from things you're going to see in most living cells. Now, stomach acid is pH 2. It's pretty acid. But the cytoplasm tends to be around 6, 7, in around there. So maybe of more relevance is to ask, near neutral pH, what forms do they take? Given the pK of the carboxylic acids, above pH 4, you're going to tend to have the carboxylate form, the deprotonated form. And given the pKa of the primary amine, it's going to tend to be protonated in that near neutral range. And so one of the things you should take away from this is that protonated and ionized are not synonyms. Whether being protonated ionizes you or not depends on what the group is. Okay? So here's a carboxylic acid. It's the protonated form. It's not ionized. If you raise the pH on it, it will deprotonate, and now it's in the ionized form of a carboxylate, a negative charge. Here's a primary amine and a basic pH. It is not protonated. It is deprotonated. It is unionized. If you drop the pH, if you increase the amount of protons around, it becomes protonated. It becomes ionized. So protonated, unprotonated is not the same as ionized, unionized. You need to know the group you're talking about to know which of those is which. Any questions about that before we move on? At one level, it's very simple. At another level, oops, I'm sorry. At another level, it's something that tends to be easy to trip over your tongue. So don't feel shy if it causes questions. Now, one of the nice things about weak acids and weak bases is that their capacity to be partially dissociated allows us and allows the cell to control the pH of a solution. And that looks something like this. If you add hydrochloric acid to straight water, it will completely dissociate, and you're going to get a large change in pH because there are a lot of protons dumped out. If you add hydrochloric acid to a solution in which there is some acetate present, the acetate can pick up, oh dang, I think I know what happened here. The acetate can pick up some of those protons and have a relatively smaller change in pH. And that turns out to be important because it allows us a range in which there is a smaller change in pH than there is in the concentration of whatever it is you're adding to it. And this is an example of what's called a titration curve. And we're comparing, this is an acetic acid titration curve. So we're starting off, say at this end with just acetic acid. pH is here in the acid range below 3. And we're going to be adding to it some sodium hydroxide, some kind of a base. And we're watching the pH change as we add base, as we eat up the protons. And I think what you can see is that in this mid-range here, the pH is not changing as much as we are changing the proton concentration. So this is the range of effective buffering. And it turns out that this inflection point at the midpoint, the place where it turns from curving upward to curving downward, this inflection point turns out to be the pKa for the acid. And at that point, half of it will be protonated and half of it will be unprotonated. It's in that range around the pKa that you get the most effective buffering because you're going to get the smaller change in the pH when you add acid or base. Okay. And it's after 420. You're certainly welcome to look at the last material on acid base in humans, but I wouldn't dwell on it too much. Okay. See you all Wednesday.